Okay, thank you for Clement to give a very nice, descriptions for the study designs, especially how to get the measurements at each endpoints and how to define those variables, and for the sample size consideration and the power calculation. Okay, so I will pick up from here and to talk about the details of some statistic analysis here. Okay, so yeah, so actually Clement has finished all this, how to, formulate a research question and have this test and data collection. And then I will talk more about the distribution of the variables, and then the statistical method will be used. And for this talk, actually, we'll only emphasize on some introductory statistic methods, such as t-test. I think Clement also mentioned that t-test, and the non-parametric version of the t-test, like a Mann-Whitney test, and Wilcoxon test, and here chi-square, and the one-way ANOVA, and the simple linear regression, and so on, and also to use the SPSS and the SAS. I will try to use both, and here we do not have SPSS and the SAS installed, but I will give you some SAS program and the SPSS pictures to show how we can use SPSS and the SAS to conduct those statistical analyses. And okay, so as we mentioned, like Clement mentioned, all these statistical methods are dependent on the variables. Okay, it's really dependent on independent variables and the dependent variables. Okay, now if there is only one population, okay, like one group of the data, and then it's dependent on the outcome variable, like the dependent variable. If the dependent variable is continuous, we can certainly use just one simple t-test to compare the average value. Okay. Now, if the outcome variable is a categorical, just like like categorical variable, like success and fail, and then we can use chi-square test, chi-square goodness fit test to test how the differences between the observed and the expected counts by using chi-square test statistics. This is the simple case with only one population, one group. Okay. Now, suppose there are two group comparison. If there are two populations, and if the outcome variable is a continuous variable, so we'll use the independent simple t-test. Okay. So but if the sample size is smaller, and if it doesn't follow the normal distribution, we may have to use the non-parametric test, like a Mann-Whitney U-test or the Wilcoxon test. If the data, but if the sample size is large enough, okay, and then as you know by the central limit theorem, right, the average value is always converged to the normal distribution, so we're not that worried about the distributions. Yeah, okay. And now suppose for the for the independent variable is two matched group, okay, two population, actually it's one population but two matched group. They are related just like pre and post. So there is dependencies, okay, between those two groups. So in that case, we cannot use the independent simple t-test. Instead, we have to use a paired t-test. Okay, paired t-test for the continuous variable, and for the categorical variable, we can use the repeated logistic regressions. Okay, and for the continuous variable, yes, we can also use the the mixed model, like mixed models for that. And paired t-test, just a special case of the mixed model with only 2 time points. If we have more time points, and we can certainly apply by using the mixed models. Okay. Now, if we have more than 2 groups, like 3 groups comparison, and we may have to go to the one-way ANOVA, and we're going to do that today. We'll cover this today. And okay, now if we have more than one independent variables. Okay, so in that case, we need to consider some models. If the outcome variable is a continuous or ordinal model, we use the linear regression or Poisson regression if it's ordinal, counts data. And if the outcome variable is binary, okay, like yes or no. So in that case, and we have many of the independent variables, and we use logistic model as we mentioned, or we may use the repeated logistic model as well. Okay. So again, all these statistical methods are all depend on the distribution of the data, the distribution, the type of the data. Okay. Yeah.
Do all those assume equal variance?
We're going to talk about that. Yes, that's a very good question. Okay, so yeah, all the with equivariant we have certain tests. Without if the assumption of the equivariant failed, and then we use different approach for that. Yeah, we'll talk about that. Yeah, good question. Yes. Okay. So again, and we just follow, Clemens mentioned that before we, begin with the descriptive statistics, to, give some report as what's the, mean, standard deviation, and the confidence interval, and for the continued data, and for the categorical variable, we do whatever counts a percentage, try to give those descriptions for that. And then we move to the bivariate analysis. I usually always suggest researchers, to do the bivariate analysis first, okay? If those two variables, if not then related, there's no need to put into the final model usually, okay? So I always suggest, people, will do the, bivariate analysis first to find out the significances, okay? If there are many variables, and then, we do some bivariate analysis. If both are continuous variable, we run the correlation. If one continue, and then with group variable, we do the t-test, and when we ANOVA, and so on. And then as the last stage, we're going to run some statistical model. And here I just talk about the linear model, linear regression model, and then we'll talk about the more advanced statistical model, such as structure equation model. Yeah, for the next. Okay. Now, I will begin with a very simple example here, and we talk about, the randomized control experiment design for the two groups here, okay? So the idea here is try to compare the new methods, okay, for, what make the improvement of the math grades here, okay? So just like we, those subjects are randomly assigned into two groups. One is the treatment group, or new method, or new drug, sometimes called new drug, and then, the control group is placebo group, okay? So, and just, ordinal training group here. Now, after they trained, okay, with these, methods, okay, and the treatment versus control, and then we record the values, okay? Here is the math grades, okay? So, and okay, so this table shows, oh, sorry. So this table shows, just present those simple data with two groups here, treatment versus control groups, okay? Yeah. So here is the t-test. We use the t-test to compare the significant difference between, the average values in terms of the two groups. Now, as you mentioned that there are two different types of the t-test here. One is the equivariant assume the t-test, okay? So we follow, we use this, yes, formula, and the equivariant not assumed, and we use this formula with two different type of degree of freedom, and we also need to test that by using the variance test. Okay, we run the SPSS or SAS, and it will run the variance test for the equality of the variance first, and then we can make choice, to see which t-test we're going to report. Yeah. Okay, so here is the. Okay. Yeah. Yes. Okay. So for even to run the t-test here, we also still need to check some normality, as I mentioned, and to check the, to see if the data is normal distributed. And then we will do the normality test first for the smaller sample size. Like for this example of the data sets, the sample size is less than 30. So we may need to, check the normal distribution first. Yeah. So here is the data in SPSS, and I'm going to, to talk a little bit about how to use SPSS. The good feature of the SPSS is like that, okay? We can import the data, for the categorical data in a numerical format here. It's the numerical variable here. And we can also define the value neighbors, okay? So in that case, which means we can install all this information in SPSS, yeah, and then generating a nice output with those value neighbors, okay? So in SPSS, if we go to the variable view window, we should be able to define all these, value neighbors, so-called value neighbors, okay? So here I present the data in the numerical format and also in the, value neighbor format here. Okay, so in SPSS, and we can run the independent sample t-test, okay? So yes, in SPSS, there is an analyze menu here. Whenever you click analyze menu, all the statistic procedures are all listed, okay? Now, compared to other program and compared to SAS or R, for SPSS, we do not need to remember all the syntax, okay? And you can just go to the, GUI, just use GUIs and go to the drop-down menu to click on Analyze, Compare Means, and then, check the, independent sample t-test. And then just follow, the steps and then put the dependent variable as the test variable and to define the grouping variable, one for the, treatment, the other for the control, and then you can run the t-test here. Okay, now here is the output. So you can see that the first table gives the discrete statistic for both groups, okay, for two groups respectively. And from this output, you see that there is average value differences, okay? But in statistics, we like to know those differences are significant at 5% confidence, at 5% error or not, okay? So we always compare the p-value with 5% significant level here. Okay, now, and again, which t-test we're going to use there? There are two different types of the t-tests here. Actually, those two values, two t-test statistic values are very close. Usually, those two values are very close, okay? So we use the Levene test to test an equality of the variance, okay? Now, for this example, since this p-value is greater than 5%, so the non-hypothesis of the equal variance is not rejected. So in that case, we can use the first t-test, which is equal variance assumed. We use the first t-test, and here is the test statistic, and the 28 degree of the freedom with the smaller p-value, so the non-hypothesis is rejected. The non-hypothesis is rejected, which means there is significant difference between those two groups. Okay. Again, and we mentioned that we may want to check the, the distribution of the outcome variable. Thanks, Clement. I know you have another talk. No. Okay. Yeah. So here we also mentioned that we can also use SAS to run the program, okay, to run the, independent sample t-test in compared to SPSS. And in the SAS here, first of all, we need to import the data. In SAS, usually we do not have the data in spreadsheet, but we can import the data into SAS system here by using this plot import command. And then we can check the, the assumption of the normal distribution by using plot univariate here, okay, and then we select the QQ plot for the outcome variable of the math by the group. So basically, we're going to check the, the normality distribution for two individual groups here, two independent groups, okay. So here is the output by using the QQ plot. Okay, now those two QQ plots look like close to straight line, okay, which is closer to the normal distribution. However, the test statistic, for one group is rejected. You can see that those p-values are more than 5% for one group, but not for the other group, okay? So in that case, due to the, smaller sample size, which may, it is worth to check, to use the non-parametric test to check it, okay? So we run the t-test first, and then compare the results with a non-parametric Wilcoxon rank test, also called a Manwini-U test here. But we run the t-test first, okay? So in SAS, the command of the t-test is plot t-test here, and then the variable here is the testing variable, is the outcome variable, and the class, and we put a categorical variable group here for the t-test. Okay. Again, in the SAS, the output also give us the test of the equivariant here, and which is non-reject. Okay, the equality of the variant is non-reject, and then we can use the pooled t-test here, and those are the same t-statistical value you saw in the SPSS, and then we do the analysis of the t-test of the equal means is reject. The analysis of the testing of the equal means is rejects. So the conclusion is, okay, the mass grade of the two methods are significant difference. Okay, so the new method has, will make the mass grade much higher compared to the, ordinal method at the 5%, error significant level here. Yeah, okay. Now, since, as we saw before, one group failed the normality test, so it is worth to check with a non-parametric test. Okay, the non-parametric test sometimes it's called the Mann-Whitney-U test. Sometimes it's called the Wilcoxon test. Actually, those two tests have the exactly same numerical test statistics, so they are equivalent. Okay, so in SAS, yeah, we have we use the plot non-parametric command, one-way command here, and we have the the test variable. Test variable is the outcome variable, grouping variable here. Okay. Now for the non-parametric measure here, okay, we have we do not need assumption for the distribution, but we still need the assumption for those observations. They are independently identically distributed, so-called IID distributed, and then the shape of the spread of the distribution are the same. So which means those two populations, two groups came from the same distribution, even the underlying assumption of the distribution is not that important, but we still assume those two populations have the same distribution shape here. And then we can run can use the non-parametric test here. Okay. So the non-parametric test is calculated based on the rank, but not the actual values. Okay. So basically, in calculation, for the non-parametric approach there, they rank the data from rank 1 to the highest rank, and then do some calculation based on all these ranks there. Okay, so, and in the non-parametric test there, they also calculate some asymptotic, t-test and the z-test statistic. Okay, for this example, both z and the t-test has very small p-values, and then the analysis is reject. But the more important is here we have the exact test of the Mann-Whitney-U test here. This is exact test based on certain mathematical calculation. We'll be able to get the distribution of the exact test and to calculate the observed p-value here, which is also less than 5%. So the analysis is reject. Okay. Now suppose we have more than two groups here. Yeah. Okay. So we cannot use the t-test, right? If we have the 3 and more groups, and we may need to consider the one-way ANOVA just to compare means, but for more than two groups like 3 and more. Okay, so we're going to use one-way ANOVA, this so-called one-way ANOVA. So, and I will give an example based on a real data, a sample of a real data, which is the current population survey of 2009. I make a random sample of the 100 observations out of the huge population, and then input the data into SPSS and SAS to do some statistical test. So again, the analysis here is assume that all the 4 geographic regions have the same average incomes. Okay, have the same average personal total income. Yeah. So there are two variables. Actually, one is personal total income. The other is the family income. So we're going to test the personal total income, okay? So my null hypothesis here is assume, okay, there are 4, geographical regions, and assume they all have the same, personal total income. And then the alternative hypothesis is no, they are not the same, okay, which means they may have 1 or 2 pairs have significant difference in terms of the, average value of the personal total income here, okay? So here is the data in SPSS spreadsheet. I will show SPSS procedures first, and then to show the SAS program. Okay, in SPSS, it's also under the Analyze menu. We click on Analyze, Compare Means, and then one-way ANOVA. And then you put the test variable as the dependent variable, which is PTOTINC, stands for personal total income. And then the factor variable is the grouping variable. Here is the region, okay, with 4 regions, okay. And then I click on the, I clicked on the option menu and try to get the discrete statistics. And for the 4 groups, okay. So here is the SPSS output. It shows the average value, standard deviations, and the confidence intervals for all these 4 geographic regions, 4 groups, and then with the F-test, with the one-way ANOVA test here. Okay. Now, for this example here, the F-test statistic is small and p-value is large compared to the 5%. So the null hypothesis is not reject. Okay? So the null hypothesis is not reject. So in that case, we conclude that there's no significant difference among the 4 groups. Okay, okay? Now here, there is no robust test of the equality of the means. Okay, this is a asymptotical F distribution, and which means if the equivariant is not assumed, so we use this robust test of the equal of the means here. Okay, and in SAS program, I'm going to show how would you to test the equivariance by using SAS program here. Okay. Now this can be displayed by using the arrow bar of the with the confidence interval of the 4 groups here. And in SPSS, we go to the graphics menu and click on the graphics, next see dialog, arrow bars, and then you follow this. Just follow the picture. Actually, you do not need to remember all this procedure, but you can just just by nature just follow those procedures, arrow bar, and then click define, click a simple arrow bar, and then define. Click define, and then dependent variable and the grouping variable, and then you can just run those arrow bars. Okay, so this is the confidence interval for those 4 groups. Okay, since there is overlap of those 4 confidence intervals, right? So it shows there's no significant difference among those 4 groups in terms of the average of the personal total incomes. Okay. And now the next picture shows that the arrow bars with significant difference. Okay, here I still compare the personal total income, but over 3 age groups. Okay, so I make the young group here, middle age and older age here. Okay, so you can see that those group 2 and the group 3 have significant higher personal total incomes compared to this younger group, okay? But there's no, significant differences between those 2 groups, okay? But, there's no overlap of the confidence interval with group 1 to group 2 and 3, but there's overlap with group 2 and 3 here, with the middle age group and the old age group here. Okay, we can run the SPSS, and then we can check the multiple comparison there, and it shows that there is significant difference between pairs, and no significant difference between those 2 pairs here. Okay. Yeah. Now the next, I'm going to show how can we run the SAS program for the one-way ANOVA. Okay, and for the SAS, yes, we always need to use the program to do. Yeah. Okay, so we use the GLM, general linear model. GLM stands for general linear model, and data equal to test. Suppose I have input the data here, and the class and then followed by the grouping variable. Here is region. And the model is the SAS command, and then, dependent variable, personal total income equal to region, and which is independent variable, okay? If you run the regression, you use the same, you can use plot regression, you can also use the plot GLM as well, okay? Now, since we're going to run the one-way ANOVA, we like to do the multiple comparison here. So we add the options command of the means and the region. We like to display the discrete statistics for the 4 groups, and then to do the multiple comparisons by using the Tukey method here. So this option of the Tukey method to do the multiple comparisons, okay? Now, actually, okay, if we get the non-significance and for the F-test here, okay, because there's no significant difference of the, among 3 groups, and in terms of the personal total income, by using the F-test statistic, there's no significant difference. There's no need to do multiple comparison, okay? Yes, so yeah, if there's no significant difference, so there's no need to do multiple comparison. Instead, here, if I run this, grouping variable as the age, you will see there is significant difference. Okay, so in that case, it was to run the multiple comparison here. Okay. Yeah. Okay. Now, and this slide shows the test of the homogeneity of the variant for the one-way ANOVA for the 4 groups here, and the hypothesis is not reject. Okay, it's not reject. So we can still use the, just the normal observation, and then use the homogeneity assumptions, and one-way ANOVA use the F-test. Okay, use the F-test here. Okay. Yeah. Okay. Now we also similar to the t-test here for one-way ANOVA. They are all based on the distributions of the normality of the dependent variable, the distribution of the dependent variable. We all assume that the dependent variable follow the normal distribution, especially for smaller sample size. Okay. Now, since this is a survey data, the sample size for this example is quite large. It's 1,000. Okay. So we always get good power. The sample size is large. If it's significant difference, we always have the power over the 80%. But it's worth to check. It's still worth to check the distribution. Okay. As you know, usually the income data do not follow the normal distribution, because the personal total income, the income data usually is truncated to the left-hand side. There are many of the lower values, and then some of the outliers on the right-hand side in terms of the histogram of the normal distribution. So usually those data fail the normality test here. Okay. So this is a SAS program again to check the the normality the normal distribution here, and then this p-value is all smaller than 5%. So the normal distribution has been rejected. So we would like to try to use the non-parametric version of the one-way ANOVA. Okay, so the non-parametric version of the one-way ANOVA, this is also Wilcoxon test here, and then the test variable still personal total income, and the class variable is region. So we use the non-parametric test, which is plot non-parametrics one way, and then test variable is the personal total income, and the class variable is of the region. So we run that, and I think we have the same results there. Yeah, Kruskal-Wallis test shows that the p-value is also greater than 5%. The hypothesis of the equal, it's not equal mean now, it's equal median, it's non-reject. Okay, if we run the non-parametric test, we're not going to test the equality of the average value of the mean, but the equal median here. So it's non-reject. Okay. Now this slide shows, okay, those box plots shows the median plot for by using a non-parametric test shows median plot here, and you can see that there's not much differences among those 4 groups. Okay, there's not much differences among those 4 groups. Yeah. Okay. Now the next model we're going to talk about is the simple linear regression. Okay, talk about a simple linear regression here. Yeah. So there are 2 variables. Both are continuous variables. Okay, both are continuous variables. Okay. For example, and then the outcome variable here we use is also the average of the personal total income by year, and then the x variable here is years of education. Okay, so I aggregate and the preview, the spreadsheet data, and by the years of education to make the average value of the personal total income by years education, and then to apply the linear regression model. The reason is like that, as I mentioned, the income data usually does not follow the normal distribution. But if I aggregate the data by years of education, okay, I calculate the average values per years of education. So based on central limit theorem, the average value converge to the normal distribution. Okay, so in that case, we can get very nice of the model fit for the linear regression here. So you will see the R square is above 90% here. Okay, so the linear regression, the equation is a line equation here. Okay, yeah. So we try to analyze how impact of years education on the personal total income here, and then we can calculate the predicted value based on the estimate of the beta coefficients, based on estimate of the beta coefficients to calculate the predicted value here. Yeah, okay. So for the linear regression, I will present the SAS program here. Yeah. Okay. So we can use plot GLM, and we can also use plot regression. REG is plot regression here, and data equal to edu. I import the educational data here, and I use the title command and the model, which is the personal total income equal to the years of education, and I'm going to plot the the personal total income versus years education, and then to do the residual plot here. Okay, so again here I will also need to check the residuals. Okay, the assumption of the linear model is that the residual has to be normal distributed and has to be independent with the predictors, with the independent variables. So I will use scatter plot of the residual versus the independent variable to check if the residual is random distributed. I will also run the QQ plot, the straight line plot, to check if the residual is normal distributed. Okay. Yeah. So this is the output. Okay, based on the regression. This is output based on regression. So you will see that the R square, okay, is about 94%. Okay, 94% of the R square. So it's very high here, and the estimate of the beta coefficients here is also significant with very small p-value here. Okay, so in the plot regression, I save the output value here. In SAS, I create an output data file, so-called a myout here, and to store the residual value, and to further to check the the normality plot of the residuals. So for the plot univariate, so the data at this time is equal to the output data set from the regression procedures here, and we're going to check that if the residual is normal distributed or not. Okay, so I use the QQ plot to check that. Yeah, I use the QQ plot, and then to find out that it's close to a straight line. Usually I would say it's okay. According to this QQ plot, we say yes, this residual is close to the straight line, and which means it follows a normal distribution. Okay, the residual does follow the normal distribution. Okay, now how do we interpret the results? okay, from the linear regression here. So yeah, we have to estimate both intercept and the slope. So I plug in the intercept and the slope to make the predict regression equation here. Yeah, predict the value. So yes, so I use the estimate, intercept, and the slope, and to write out a predict equation here. So for example, because here this is negative value, okay, some people may argue, okay, why you get the negative intercept? Why? Yeah, it's because, okay, and what's the intercept here is the value when the year's education equal to 0, right? Yeah, so that's why. And sometimes people like, you know, to make a center of the independent variable, okay? If I make a center of the independent variable, I use this, you know, years of education minus the average value, and then this intercept will be a positive value, which is the estimated value when the, you know, years education is the average value, okay? So that will make more sense, yeah. So that's why here I will try to calculate those predicted value. For example, if the years education is equal to 12, yeah, so I plug in to this, you know, predict equation to do the calculation. Okay, this is equal sign. Why become the minus sign here? So we predict the personal total income is about 35,000. Okay, so it's positive value. Okay, yeah. So if this x equal to 0, then you get the negative value. But usually this never happen of years education equal to 0. So yeah. Okay, so the R square is the 94% again, which means years of education explained almost like 94 of the variations of the personal total income. So this is a very strong relationship, okay? If I just do the, you know, if I use the subject data, okay, do those scatter plot, I will not get that strong relationship, okay? But for this example, I use the aggregate data by the years of education, so get a very strong relationship. You can see from this, you know, regression plot here. In the SAS and in a plot regression command, I made an option there to ask for a regression plot here. So we have the fitted regression line, yeah, across those scatter plot, those pairs here, and it also shows R square, yeah, which is 94%, and then, you know, those, you know, predicted regression equation is here. Okay, so this is a, you know, regression plot, a linear regression plot here. Yeah. Okay. Now next, I'm going to move to the chi-square test. Okay, before and up to now, all the outcome variable are all continuous, right? All the outcome variable, personal income and then the math score, they are all continuous variable. So we use the independent sample t-test, one-way ANOVA, and the linear regression. Okay, so the next topics, okay, we're going to study, it will be the chi-square test. So here, actually, you can consider one is outcome variable, the other is, you know, and the independent variable, or you could just say to check the relationship between two, you know, categorical variable here. So chi-square test, actually, it is a non-parametric test. Okay, it's used to test the association between two categorical variables, to test the association between the two independent variables. Okay, so the non-hypothesis here is slightly different from before. Okay, and for the previous, you know, statistical procedure like a t-test, one-way ANOVA, usually we say, okay, the, you know, average value is equal, or if the, you know, estimate of coefficient is equal to 0. Okay, but for the chi-square test, the non-hypothesis is, you know, there is no association between two variables. Okay, so that's the non-hypothesis of the chi-square test, which means those two variables, column variable and the row variable, are independent. Okay. The alternative hypothesis is there is association between two variables. There is association between two variables. Okay, so the chi-square test statistic is calculated based on the assumption of the independencies. Okay, under the non-hypothesis of the independencies of the column and the row variable, okay, we can calculate the expected value. We can calculate the expected value is the, you know, row total times column total divided by sample size here, yeah, and then we sum all these differences, okay, between the observed value and the expected value. We sum all the differences between observed and the expected value, and to get the chi-square test statistic, okay? Yep. And according to this formula, you can see that the chi-square test statistic formula, okay? So if the observed value is quite different from the expected value, which means if my expectation is wrong, okay, so these differences will be bigger, right? So in that case, chi-square test statistic value will be larger, and then the p-value will be smaller. Yes, okay. So the analysis will be rejected, okay, will be rejected here, okay. Yeah. So in SPSS, okay, to do the chi-square test, okay, again, we go to the Analyze menu, yeah, go into descriptive, and then, to ask for cross tabulation to create a two-way table first, okay, to create a two-way table first. And then we can also click on the statistical menu and the push button to ask for the chi-square test statistic. Now, in the cross tab here, there is a push button of the cells here, and we like to also to have the expected value and the no percentage. And then we can click on the statistic if you run the SPSS to ask for the chi-square test here. Okay. So here is the output, okay? We have two variables here. We try to test if there is any association between gender and the personal total income, okay? At this time, the personal total income is a categorical variable into three categories: lower, medium, and high income, okay? So it's a categorical variable with only three values. And then we try to test if any association between gender and then the personal total income. And also, we can try to test in terms of percentage, okay, in terms of percentage. And the analysis can be said that there is, equal probabilities of the higher income for both male and female, and the alternative thesis is the proportion are not the same here, okay. Now, if we check this two-way table, we see that for the female subject there, for the female subjects, there is 7.6% of the observations in the category of the higher income compared to male. There is about 19% of observations in the category of the higher income, okay? Now, for the lower income here, and for the female, it's about 54% in the category of the lower income, but compared to the 40% of the male in the category of the lower income. Okay, so you can see those percentages are quite different. Okay, so by guessing, I would say yes, there could be some association between gender and the personal income. Okay, so I run the chi-square test statistic. And which is in the next slides, okay, it shows there is, significance, okay, there is significance of the chi-square test statistic here. Yes, okay, so I do the calculation. Actually, SPSS can do all this calculation. SPSS or SAS can do all this calculation, and we get the chi-square test statistic is about 34, and then with the 2 degrees of the freedom, and then this is rejected, which means there is association between gender and the personal income, yeah. Okay, and yeah. Yeah, so that is in SPSS, there's SPSS output here. Yeah, and in SAS, I just quick to show the SAS program, and for the chi-square test, which is in the plot frequency command and the table, which is 2 categorical variable, gender, sex, and income. Here, the income is in 3 categories, and we ask to get the expected counts and the chi-square test statistic. So that's the SAS output, which is quite similar to the SPSS output here. Yeah, just in different format, but same numbers here. Okay, I think I used all my time here, so still have 1 minute left. If you have any questions, do you have any question? If not, we save the question toward to the end. Okay, thank you.